Well, congratulations if you've made it this far. We are now going to enter the modern era of cryptography. We're ready to start talking about public key encryption. This is a pretty big deal, and you'll see why as we go through this material together. So everything we've done so far this semester has always been about private key, or what is a synonym, symmetric encryption, okay? And affine and Hill encryption are examples of private key schemes. And Diffie-Hellman key exchange was designed to actually accommodate the creation of keys for private systems. So everything we've done so far has been private. This is getting ready to change as we start talking about public key systems, our first one being El-Gamal, which will be the next module. And the point of this lecture is to sort of talk about the differences. I find it very helpful to talk about public key encryption in general before doing El-Gamal, because otherwise it's confusing as to how it operates and why you would do it. So let's just talk about public key encryption as an idea before we get any further. To do that, we need to talk about private key schemes a little bit more and to understand sort of some of the restrictions on how they're built. So in a private key system, again, you should always think like affine encryption. Every pair, it's important, every pair of users has to agree on a common key before any communication occurs. So like in our model for class, when Alice and Bob want to communicate, they first need to generate a common key. Let's call it K1. But what if there's a third person, Carl, around? Well, then if Alice and Carl need to communicate, then they have to generate their own key. That's a different pair of people than Alice and Bob. So every pair needs a key. So they have to generate a different key, K2. But then what about Bob and Carl? Bob and Carl also need their own key. And so that generates another shared key, K3. And so with three people in your network, three symmetric keys must be generated. So the question would be, how would this scale up, right? Three people is not a reasonable size or a realistic size of a network. What if you have 100 people on your network, or 250 people on your network, or 1,000,000 people? How would it scale, right? So for a baby step example, let's look at example 1 where suppose your network has only 4 people in it. Alice, Bob, Carl, and Denise, right? So how many keys must be generated for all these people to participate in a private key scheme? Well, just write out all the ways to make pairs. Alice and Bob, Alice and Carl, Alice, Denise, Bob and Carl, Bob and Denise, and Carl and Denise. There are 6 ways to do that. So a network of 4 people would require 6 different keys, one for every couple. Okay? And there are some simple combinatorics here that gives you a nice clean formula for this, no matter how many people you had on your network. For instance, if you had n people, your job is to count all possible couples, P1, P2, all pairs of people from the group, right? Well, there's certainly n different ways you can choose the first person, right? And then you don't have an Alice Alice or a Bob Bob, right? So once you choose one person, they're out of the pool, and there are n minus 1 ways to choose a second person, right? So this seems to give n times n minus 1 possible pairs of people, but that's wrong. And the reason it's wrong is because Alice and Bob are the same couple as Bob and Alice, right? So the pair of people P1, P2 is actually the same people as P2, P1. In other words, the count n times n minus 1 accidentally counted every single pair twice, so it's wrong by a factor of 2. It's a double count. So the way to fix that is to divide it by 2, and that's the right answer. So that gives us proposition 1. If you have a network of n people and you want to know how many keys you must generate for all of them to be able to participate in a private key system, the answer is n times n minus 1 over 2. And notice that this gives the correct count for our previous network of 4 people. With 4 people, that would give 4 times 3 over 2, which is indeed 6 keys required. Okay? So I want you to try this yourself a couple of times. Use this proposition to solve these problems. How many symmetric keys do you need for a network of 18 people, and how many keys do you need for a network of 100 people? Right? But now let's look at an even more realistic scenario. Suppose you've already set up your network of 4 people. So you have your 4-person network, and that 4-person network, as we said, needed 6 keys, right? But then you hire a 5th person, Edward, right? And that person needs to be added to your network. How many keys must you add to accommodate Edward? Well, all you got to do is give Edward a key to match every one of the 4 people. You need an Alice Edward, a Bob Edward, a Carl Edward, and a Denise Edward. So you only got to give 4 more keys. So all you got to do is generate 4 more keys to accommodate one person, right? One for all of the 4 pre-existing people, right? You can also get that by counting the keys you would need for 5 people and subtracting it out from the keys you already knew that you needed for a group of 4. So you have to count for 5 and count for 4, and lo and behold, the difference is 4, okay, as you would expect. Right? So I want you to try that again. What if you had a network of 100 people and then you hire a 101st person? How many new keys must be created? And just answer these questions in the associated Canvas quiz. Right? So now I want to talk about what is different about public key schemes, right? So now let's change gears and talk about public key encryption. Now you're going to find this really, really different from private systems. And in fact, you might even find it weird or bizarre or even hard to believe that such schemes even exist and are possible and are safe. They are, but you got to sit tight. We've got to learn this stuff first. It's kind of a miracle that public key systems even exist and are safe for use. But let me tell you what a public key system is. So here's one stark difference. In a public key system, each user has their own key data, and it has nothing to do with anybody else. Okay? So Alice has her own key, and that's got nothing to do with Bob, Carl, or Denise. And Bob has his own key, and it's got nothing to do with anybody else. So this has got nothing to do with pairs of people anymore. Each user's key has 2 pieces. One part of the key is used for encrypting, and the other part is used for decrypting. Okay, here's the important part. The encryption key is made public. Anybody in the world can see it and use it, even Eve. That's where the public and public key encryption comes from. But not everything is public, okay? The decryption key, however, is private. Nobody on the planet knows the decryption key except for the user. So only Alice knows Alice's decryption key. Who knows Alice's encryption key? Everybody. Okay? Why would we want this? How would it even work? Let's talk about this. Suppose Alice's key data is ED, okay? Where E is public, and that's used for encryption, and D is private, and that's only known to Alice, and that's used for decryption. Okay? Suppose Bob wants to send Alice a message. Okay? Here's what Bob does. Bob looks up Alice's public encryption key, which anybody can do because it's public, and he uses Alice's own encryption key to encrypt the message. He then takes that ciphertext and he emails that to Alice. Okay? Next, Alice uses her own private decryption key to decrypt the ciphertext and recover Bob's original message. Do you see how this works? Anybody in the world can encrypt a message and send it to Alice because her encryption key is public. But who can take that and decrypt it and see the original plaintext? Only Alice can decrypt, since she is the only one that has the decryption key. The decryption key D is private. Only Alice knows that. This is kind of a miracle that this stuff even exists. Okay? So there are some things that are worth pointing out about this. First, please take note of the asymmetry. All right? Public key schemes are also called asymmetric encryption schemes. When Bob wants to send a message to Alice, he must use Alice's key. This is always, always, always about the recipient of the message, not the transmitter. Okay? When Alice wants to respond to Bob, she must use Bob's key, not her own. So you're always changing keys because it's about the recipient, not the transmitter. Okay? So when Bob wants to send to Alice, he uses her key. When Alice wants to send to Bob, she must use his key, which is different. Right? Secondly, anyone on the planet can encrypt a message to Alice, including Eve. Does that sound dangerous to you? It does to me. You are now allowing the enemy to send you encrypted messages. You are now allowing the enemy to execute a chosen plaintext attack. That's very dangerous. Is it still safe to do this? Thirdly, it seems scary to me that E is public but D is not. Right? After all, they are related to each other. D is the inverse of E. Whatever E does, D unravels it. So is it possible that you could derive D from E? If so, that's bad. E is public and everybody knows it, and D is supposed to be private. So if you can obtain D from knowledge of E, that would be bad. So there's all kinds of good questions here. Here's the biggest point. Finally, note that this model of public key encryption is exactly what you want for e-commerce. Alice is Amazon. Okay? Amazon has a public key for encryption, and you can use that to encrypt your credit card data. In fact, that's what your web browser does. Anyone can use that public encryption key to safely send Amazon their credit card information. Okay? However, Amazon is the only one who can successfully decrypt it and see your true credit card number charging the right account. right? Eve can see the encryption happen. She can see your credit card number encrypted, but she cannot decrypt it and defraud you because only Amazon possesses the decryption key. So this allows anyone in the world to participate in e-commerce with Amazon, and that's good, and do so safely. That's good, right? So beyond this idea of using public key encryption for e-commerce, it's also incredibly efficient when it comes to networks and key generation. So let's think about our network of 4 people from before. If you remember before, they needed 6 keys to participate in a private scheme. But how many keys would they need if all 4 people wanted to participate in a public system? Well, only 4, because everybody needs their own key, and that's it. There are no more couples. There are no more pairs of people, right? So with 4 people, you need 4 keys, 1 for every person. With 5 people, you need 5 keys, 1 for every person. With 1,000,000 people, you need 1,000,000 keys, 1 for every person. And what if you had 4 people, but then a 5th person, E, wants to join in? There's Edward again. How many additional keys must you create? Well, just 1, since all you got to do is give Edward his own key. Everyone else is already accommodated. See the difference? So I want you to try exercises 4, 5, and 6, okay, which echo exercises 1, 2, and 3. But 4, 5, and 6 are now taking place in a public key system, whereas exercises 1, 2, and 3 took place in a private key scheme. So try exercises 4, 5, and 6. Try the quiz. If you get stuck or have questions, let me know.